This is Mrs. O'Neill for AP Chemistry, Chapter 16, Section 10, Acid-Base Behavior and Chemical Behavior. So your objective is to explore the relationship between chemical structure and acid-base behavior. Remember, the structure of your molecule, any kind of compound, any element, any metal, anything, right? If they're giving you the structure, that structure of that chemical formula is going to be so important, the most important of all the information that they can give you. So again, pause the video, fill in the blanks, and then play to hear my words. I believe I have 3 sections, so we're going to talk about each of these in a little bit more detail. So the first one, H in a molecule has to be positive. Well, if it's an acid, it definitely does. So a lot of times, and you should draw this in your notes, a lot of times they'll signify that positive to that negative end, right? Signifying that your positive H goes to the negative X, whatever that X may be. And we've seen this before when we talk about polar molecules. So it breaks up into H plus and X negative. Now remember that X negative could be a regular element, or I should say an ion with a negative charge, anion, or a polyatomic ion. And a lot of times it's signified with A when we're dealing with a weak acid, HA. However, you do know that H can also be negative. Well, if H is negative, like in this sodium hydride, then it could also act as a base. So we want to remember H plus would mean an acid and an H negative would mean a base. So how about our bond strength? Well, thank goodness we have this periodic table, because that periodic table gives us lots of trends, and it's very helpful to understand these trends. So the bond strength of acids are going to decrease going down the periodic table. Of course, the weaker bonds are going to be easier to break. So what's going on here? Why is the trend the way it is? Well, let's look at this. HF is weak. Remember, if it's weak, first of all, it's not on the list. And second of all, that means it wants to stay together as a molecule more than it wants to break apart. Well, if it wants to stay together more, that means its bond strength is big. However, if we look at HI, if we compare HI to HF, HI is very strong acid. Well, that means that it wants to break into ions. If it wants to break into ions, that means its bond strength is very small, right? It doesn't mind being away from each other. It'd rather be as ions than together. So you also want to think about the size, right? Iodine is much larger than fluorine. So again, it's going to be easier to separate from the molecule. That bond strength is going to be very small because of the size of those atoms. How about the stability of that conjugate base? Well, again, think of it this way. The greater the stability of that conjugate base, the stronger that acid, right? Because that conjugate base wants to stay as a conjugate base more than it wants to be part of that acid. Okay, so in other words, and this is also in your notes, we want to remember strong when we're dealing with acids and bases means breaking apart, and weak means that it wants to stay together or stay as is. And I say stay as is because I'm going to show you a chart in a moment. This is also in your notes. So if we think about HCl, HCl is very, very strong because it wants to break up into ions. It doesn't like to stay together. So the more it wants to stay as an ion, if we're talking again about the stability of the conjugate base, the more it wants to stay as an ion, the weaker that CB is going to be, right? Because it wants to stay as is. It wants to stay as that ion. So they give us a nice little list. They might give this to you, but what you really want to remember is the stronger one side is, the weaker the other guy is. So the stronger the acid, the weaker its conjugate base, right? The acid does not want to stay as HCl, but the base, the conjugate base, really wants to stay as that Cl minus ion. So I want you to look down here because you've seen this before. So if we look at OH negative versus O2 negative, well, this guy is very, very strong because it doesn't want to stay that way. It wants to break apart, or it wants to move on. It needs to grab that H to become that OH negative. What am I talking about? Well, this is called disproportionation. Hopefully I said that right. You know, I don't get those long words correctly. So if you pause the video and read this over, hopefully this makes sense, right? This O2 negative really is strong because it wants to grab that H from that water and form that O2, which is very, very, this is the way it exists, right? O2 exists that way. And of course, we see that OH minus, it's going to want to form that base. So again, whichever way it wants to be more, so in other words, the right side here is going to happen more often than the left side. That's going to be the weaker guy, right? That's what it wants to be. It doesn't want to break apart. So you've seen this already in chapter 7, section 7, when we talked about the oxides and peroxides and superoxides. There it is. All right, there's your superoxide, O2 -1. So you've seen it before. And we want to remember that this is an ionic compound, so it's going to want to break up into that K+1 O2 -1. Okay, and again, it's not going to want to stay that way. Just like you saw, that's a very, very strong conjugate base, and it's going to want to kick and form, hopefully there's water somewhere, and grab that water to form that OH negative. So let's look at these trends. First, there's a trends in binary acids, and a binary acid, again, is going to be H with an anion, and it's going to be a single ion or a single atom making up that anion. So again, the polarity is going to be determined by the electronegativity of that second guy there, that negative part. And remember, that's only going to be one element. So the strength of that HX bond is going to decrease as that element increases in size, which we just talked about, right? We talked about how iodine is much greater or bigger in size than fluorine. So of course that bond strength is going to be decreased. It's going to be less. So pause the video. Here's some information. So acid-base increases strength as you go across the periodic table and increases strength as you go down. Can you come up with a why as if this was a free response question and you had to give a justification? Hopefully this makes sense. If we look at our formulas, well, we go from our CH was very, very nonpolar. We go to something that's polar, but it does have a non-bonding pair, and it's also a base. Then we go to water, which is very, very neutral. And then, of course, we've made our acid, HF. Now, remember, HF is very weak. It's a weak acid. It's not on our list, but it is nonetheless, it is an acid. So as we go across, we're going to increase strength in acidity. How about as we go down? Does this make sense? Again, our electronegativity is going to decrease, so it's going to want to ionize more. Okay, and as we ionize more, it's going to increase our strength in acidity. So again, just another visual and to get you to understand that Ka. So notice the Ka values, right? As the smaller the Ka values, the weaker the acid, right? The smaller the Ka values, the weaker the acid. So can you pause and give it some thought with an answer? Hopefully you came up with that because that's what you just learned. So oxyacids, again, these are also acids, but binary just meant two elements together. Oxyacids are talking about an H with a polyatomic ion, but now those polyatomic ions have to have oxygen in them. So the more oxygens you have, the more acidic it's going to be. So this HClO4 is very, very acidic compared to the HClO. So you have 4 oxygens compared to 1. Now remember, these two, perchloric and chloric acid, those two acids are on the list. They are considered strong versus your hypochloric, this would be chloric and this would be your hypochloric acids, are not on the list. So they are weak. Okay, so what's going on? Why does this happen? Well, your strength of your oxyacids increase with increased electron density. So if you have one chlorine versus attached to an oxygen, now we have a little bit more electron density. We're going to add some oxygen. We're going to add an oxygen. So our electron density is going to increase. Okay, so here it is again, and look at our Ka values. So the smaller our Ka value, right, the weaker our acid. So as we increase our Ka value, we're going to get a little bit stronger. And of course, these guys don't even have a Ka value because they're on the list. They're a strong acid. K just represents something at equilibrium, right? Our constant at equilibrium when we have something weak. So again, give it some thought. Think about the structures. Can you put the structures together? Did you come up with something like that? Now, does the question make a little bit more sense? Again, which acid has a large acid dissociation constant? Again, think about that periodic table. And hopefully you got that as an answer. Again, read over that information. Again, oxyacids, just continuing on, just more information about the more oxygen, the higher electronegativity, the stronger that electron withdrawing, okay? And again, we're always talking about those oxygens attached to that central element. So the more polar that OH bond will be, the more acidic that compound overall will be. And then again, we can also talk about its conjugate base. So pause the video. Hopefully this makes sense as to what is going on here. It makes sense, and I even put this on here for your periodic table. But now we're talking, I know this is about the acid, but we're talking about that YOH, okay? We're talking about that hydride and what's going to happen with the OH, what's happening to the electronegativity, what's happening to our Ka values, okay? So pause and look this over. So again, going down the periodic table, what's going to happen? Well, our binary acids are going to increase in strength, and our oxyacids are actually going to decrease in strength. So how about carboxylic acids? Okay, this is that big, gigantic functional group that you learned in chapter 24. So as we add oxygen, the electron density, we're going to increase our polarity, which means it's going to help stabilize actually that conjugate base. All right, so think about that. The more stable the conjugate base, right, the more it wants to be that conjugate base. So that's going to be your weak guy. So the stronger the acid is going to be. Okay, so again, it's always opposite of what's happening. So again, we're looking here at our electron density. So that conjugate base, though, can also exhibit resonance. And if that happens, okay, that means that it's making it more stable. It wants to be more of that conjugate base than the acid it originally came from. So again, give it some thought. Hopefully that makes sense because you know that functional group. Okay, and here are some examples of them and some more examples of them. Again, I bring this to your attention because we are going to be looking at these organic carboxylic acid groups because they are acids. And again, it gives you those citric acid versus acetic acid, just showing you the groups, how they could be written, and knowing that they are weak. Again, these are two very, very acids that you will see a lot. So pause the video, fill in your chart, and hopefully this information makes sense, kind of puts it all in like a nutshell. Okay, see you in class.